Okay, guys, so a couple of announcements. So, number one, listen up, please, is Thursday we'll have a test on the unit. So, tomorrow we'll finish this thing up and I'll give you the review. That's under tomorrow. For today, you should have that packet. If you, for the people that are at home, let's see, let me get on the right class here. The blank notes for today are posted right here where it says March 8th. So for you guys at home, if you open up this PDF right here, that'll have the blank notes. What I'd like everybody to do is, though, to go to March 8th, open that up, and then there's a GeoGebra link. Click on that. And this is a good way to understand what standard deviation is.
You want everybody on there or just online?
No, everybody. What this does, standard deviation is, it's like a good visual on what you're actually calculating. Okay, so I'll give you a minute to get that open, and then we'll talk about what this is showing you. And that little applet that I had you open up is a good way to visualize it. I mean, I knew how to do standard deviation in high school. I had no idea what I was actually calculating. I just knew how to get the number. So that applet is going to explain to you what standard deviation actually is. But if you look at these two graphs right here, if we just compare the quartiles and we know that when you look at quartiles, you look at IQR, you look at range, all of those help you get a sense of how spread out your data is. Okay, now if you look at these two, the mean of both of these is 15. Here's your mean. Okay, 15, 15. Both of them have the exact same mean. All right, if you look at their medians, they both have the same medians, 14 and 14. Okay, if you look at their ranges, 26 minus 3, that's a range of 23. And down here, 26 minus 3, that's 23. So these two data sets have the same mean, have the same median, have the same range, but they look very different. Okay, this data is much more spread out than this data. Now, what gives you a hint of that is the IQRs are really different. Okay, big difference there. Okay, and then the other thing that's different is when you look at the standard deviation of these. That just says big difference. Okay, this one here has much more spread. More spread, greater variability. All of this stuff is very tight to the median. Now remember, guys, what this is comparing, this is showing you how each point is, how it compares to the median. This middle line is the median. So the data down here is much more compacted around the median. Okay, so the data is close to the median. That's what the size of the box tells you. That's a really narrow box. Remember, 50% of all the numbers are in this little box. So 50% of all the data is really close to the median. All right, now what standard deviation does It's very similar to this, except for instead of this being the median, it's the mean. Now, it's a little hard to see on here because of the shading, but the symbol for standard deviation kind of looks like a, I don't even know how you describe it, but it's like an O with a, or maybe like a whistle. Yeah, this is actually the Greek letter sigma. That's lowercase sigma. Okay, this is uppercase sigma. Oh, they're the same letter. One's just capital. This is capital sigma, and this is lowercase sigma, like a capital S and a lower s. So when you see that, this sign right here stands for standard deviation. And then down here, here's the standard deviation. So this one's got a standard deviation of 8, and this one's got a standard deviation of 5. And you can tell this one is more compact, less spread when it has a smaller standard deviation. So when you have a small standard deviation, the numbers are going to be close together. When you have a large standard deviation or larger, it's going to be more spread out. Okay, now to understand what that number actually means, all right, if we took a look at our M&M data and we just looked at the standard deviation of it, so let's see, recent, okay. So when we did this, we calculated the standard deviation. We didn't talk about what it was. All right, let's see. Oh, wait. Okay. Yes, I took roll. Got it. I got you're here, Kenan. All right. So on this graph right here, guys, let me make this a little, let's see, view. Okay, things are low right now. Okay. Well, I can't enlarge it because my, oh, there we go. Just jumped up. Okay. All right. If you look at the reds, okay, so when we go down this column of red M&Ms, okay, the average red M&M had 16 M&Ms in it. Don't go up there. Shoot. Come on back. All right. Okay, so look up here, folks. Here's the average for the red M&Ms right there. So there was 16. So on average, most packages had 16 M&Ms. Now, if you look down here, here's the deviation for the red M&Ms. It's 3.47. Now, here's how you think about it. Is most of the red M&Ms fall, if this was the average, the M&Ms would have 16 plus 3.47, whoops, or 16 minus 3.47. Okay? So basically what it's telling you is most of the M&Ms would fall between, if this was 16, and this, let's just think about this as like 3.5. Okay? Most bags of M&Ms would have between 19 and 13 M&Ms in them. Okay? The way I'm getting that is that this is 3.5, and I'm just doing 16 plus 3.5, 19.5. 16 minus 3.5, which would be what's 12.5. Whoa. Okay, so most of the packages would have between that many M&Ms in them. Now look at it for the browns. Okay, so with the brown M&Ms, each packet on average only had 3. Okay, the standard deviation for the brown ones, I'm sorry guys, computer is super laggy. Come on back. Come on, don't be scared. There you go. All right, so here's my browns. 3. On average, it was 3. And then it had a standard deviation of 1.5. Okay, so if I add 1.5, and if I subtract 1.5, what this tells me is about 66% of all packages between 1.5 brown M&Ms. Okay, all you're doing is you're adding this deviation and you're subtracting it. So the larger the standard deviation, the more variability you had in terms of M&Ms, the number. Now look at the standard deviation for the weight of each package, 0.04. That means that there was very little difference between each package and the average. So they do a pretty good job packaging their M&Ms in terms of the weight being the same. Okay? All right, now what this little applet does that you got in front of you here, okay, it demonstrates how standard deviation is done. Somebody would have shown this to me when I was learning it. Okay, each one of these dots represents a number in this list. Okay, so like right here, that number 1, that's this dot right here. Okay, the number 10, that's this dot right here. The dotted line is the average of those 12 dots there. So if we added all those up and divided by 12, we'd have 5. All right, now what this line represents is this is the length that this point is from the median. The mean, I mean. So if I did 1 take away 5, this is negative. What that means is 1 is 4 points below the mean. Below the mean. That's what that stands for, that -4 right there. Yeah. Yeah.
Can we have Alexis, Nathan, and then anyone else dressed up for Spirit Day to take the picture?
Sure.
We'll bring them right back.
These guys are 890s? Look like they... Oh, Will Smith, I get you. Okay. All right. Now, if you go to the 9, this 9 is this point. Okay, now if you calculate, well, how far is 9 from the mean? Okay, well, I'm going to do 9 minus 5. Okay, so what that tells, that's 4. So what that tells me is the data point 9 is 4 points above the mean. So the number associated with each one of these data points, the number associated with each data point is the distance that it is from the mean. So for example, this right here is the number 2. What's its distance from the mean? Josefina, what's the difference? How far is this from the average? Above or below? So we'd say 2 is -2 points, -3 points below the mean. Okay, if it's above the mean, it's going to be +2. All right, so what's this data point telling you? This guy. Which number is it associated with?
7.
Yep, that's 7.
2.
Right, so 7 is 2 points above the mean. All right. So to calculate the standard deviation, you have to know what the mean is, and then you take every point in your set and you subtract the mean from each one of these numbers. So I would be doing -5, 2 minus 5, and there's 2 of those. Oh no, there's 3 of them. Then I'd be doing 3 minus 5, 4 minus 5, etc. Now all of this is on the back of your paper. Okay, now if you watch what happens, this example has a standard deviation of 2.973. Now, as you take these points and you start dragging them around, what would you do to make the standard deviation smaller? I want the standard deviation to be smaller than 2.97. What am I going to do with these points? Drag them down? Smaller. Okay, so I'm dragging them down, but it's the standard deviation's getting, looks like, bigger. Oh, that one got smaller.
So you gotta make it all.
Got smaller. Where could I put them so the standard deviation is 0? Yeah. Yeah, so if you put all of these on the line that represents the average or the mean, it's real laggy, guys. So, but as these get closer and closer, where they're not very different from the average, then your standard deviation shrinks. So all standard deviation is describing is how far the data is from the average. Okay, now there is no standard deviation because every data point is the same as the average. Now, as I pull these away,
Hi, Carly.
okay, now you can start, as you pull them away, you can see the standard deviation growing. Grow that. 110, gotcha. Okay, Canton, 110. All right. So, standard deviation, all it is describing the spread from the mean. Okay, and what makes it different than box and whisker describes the spread from the median. So the more spread out these are from that red line, the bigger the standard deviation. The red line is the average of all the data. All right, so the process for doing this, if you flip over to the back now, let's see. Okay, here's how you get the standard deviation. You first calculate what's known as the variance. All right. So, I'm going to explain to you what this symbol means, all this stuff means. So, it looks like a bunch of gobbledygook. All right, so in here, sigma squared is the variance, not the standard deviation. So it's the Greek letter sigma squared. All right. This Greek letter right here, the one that looks like a U, is actually the Greek letter mu, mu. Okay? Mu stands for the mean. All right, so here's what this means here. This means take each data point and subtract the average. So that's what I did. I took the number 1 and I subtracted the average. And I got -4. Okay? So this symbol, all this stuff, all it means is take each data point and subtract the average. So I did that. I took 2 and I subtracted the average. Now the reason I multiplied it by 3 is because there's 3 2s. Then I took 3, subtracted the average. So what this is telling you here, that right there just means subtract the mean from each number in your list. Okay? And that's what's done, that's what I did right here, guys. I subtracted the average from each number in this list. And then this is what you get. -4, 3 times -3, -2, -1, 0, 2, 3, 4, 5. Okay, any questions up to that point? So, first step, find the average. Second step, take the average and subtract it from each number in this data set. Third step, square each one of these values. Okay, so that's what I did right here. Square each value that we had. So -4 squared, -3 squared, -2 squared, -1 squared, etc. Then I take all of those numbers and I add them up and divide by 12, and that is the variance, not the standard deviation, the variance. Okay, that's this number right here. And that's its symbol. So all that is, what you did here was you did the average. See, and that's what it says right here, guys. The variance is the arithmetic mean. That just means average. Okay? It's the average of the squared differences between each value and the mean. So these were the differences. -4, -3, -2. Then we squared them, and then we added them all up and we divided by. That's the variance. Now, to get the standard deviation, you just take the square root. So the standard deviation is equal to the square root of the variance. That's the number that we want. Now, there's the reason why you got to take the square root is because if you don't, the labels don't make any sense. So, for example, a few minutes ago I showed you the M&Ms. And I said for a red M&M, the average red M&M was 16 red M&Ms. And then the variance for the red M&M was like 9. Well, here's the problem. If this was the variance, the label on it is squared M&Ms. Well, a squared M&M doesn't make any sense. What do you mean squared M&M? It's an M&M or it's not an M&M. So when you take the square root of this, it becomes 3 M&Ms. Now that makes sense. I'm going to either add 3 M&Ms or I'm going to subtract 3 M&Ms. And that gives me what I'm going to find in most bags. There's going to be between 13 and 19 M&Ms. You can't add M&Ms squared to something. So that's why you have to take the square root to get the variance. All right, questions up to this point. The good news is you don't have to, your calculator is going to do the work for you. I just wanted to show you where it comes from. Okay, so all in all, the smaller the standard deviation, the closer each dot is to the mean. A really small standard deviation means all of the data is really close to the average. Now, to show you the difference, okay, right here, a small IQR, okay, just so that you understand the difference. A small IQR, the closer the data is to the median. See, this one says median, whereas standard deviation says mean. So when an IQR is small, all of the data is close to the median. When standard deviation is small, all the data is close to the mean. Okay, questions up to this point? Anybody at home? Okay. Okay. All right, let's move on then. So all this formula is here is This is the symbol for standard deviation. It's just the Greek letter sigma. To get it, you do the square root of the variance. Square root of the variance is
I think I'm good.
the standard
I'll let you know if I have any
deviation.
questions, though.
Or, if you take the standard deviation and you square it, you're going to get the variance. Square root the variance, you get the standard deviation. Square the standard deviation, you get the variance. Okay, so when you have a small IQR, we know our box is going to look like that. Small IQR, large IQR. Okay, when you have a small standard deviation, your data is going to look like this. This is data that has a small or low standard deviation. This data is more spread out because it has a higher standard deviation. More spread means higher standard deviation. Okay, some other important properties of standard deviation. Okay, so I would underline this or put a box around it. Low standard deviation shows the data points tend to be closer to the mean than larger standard deviations. Okay, standard deviation is used to measure the spread, quiet please, around the mean. So, IQR is the spread around the median. Standard deviation is the spread around the mean. So IQR compares the data to the median. Standard deviation compares the data to the average. Okay. Now, the last two that are important is standard deviation is susceptible to really big numbers and really small numbers. So when you have a number that's really far away from the mean, so okay, like 10. 10 is 5 places from the mean. Well, look what happens when you square it. This becomes 25, which is really going to affect your average. So when something is far away from the mean, it's going to have a lot of effect on this standard deviation. So this is similar to, this is a similar issue with the mean. Remember, the mean can really get affected by really big values and really small values. So standard deviation is not as robust, because if you have a really big number or small number, it's going to distort the spread. Okay, and then the last important point, if you're going to compare standard deviations, the two means have to be close to each other. Data approximately the same mean, the greater the standard spread, The greater the spread, the greater the standard deviation. So if I was comparing two data sets, I can only do it if the means are somewhat close. All right, questions up to this point? How about at home? Okay, now we're going to show you how to do it on your calculator. All right, so if you need a calculator, come back here and grab one, or open the one on your laptop. All right, what we're going to do is we're going to put in these are 10 games and how much each player scored. So in the last 10 games, this is what player A scored, and these are the points player B scored. So on our calculator, we're going to put those into list 1 and list 2. And then we're going to use the calculator to get the mean, median, the range, and the standard deviation. All right, so open up your calculator. Okay, and you go stat. So what I'm doing right now is all here on this page. Right here. So I'm going to type in player A for list 1 and player B for list 2. That should be a 39 right there. Okay, so let's take a minute and get those typed in. Okay, so I go edit, and I go to my lists, and I type in those two sets of numbers. Now I've already got them typed in from my last class, so I'm just going to leave those. Anybody need help on how to type them in? Button click, stat, calculate, one variable statistics, and we're first going to do player A. So player A is in L1. Player A does not have a frequency list, so I clear that. And then I just go down to calculate. And there's all my statistics. So as we go through this list now, so down here where it says total points, okay, so here's the sum of the points for player A. That's your sum. Remember that uppercase sigma means add up all the x's. So this player together scored 150 points. Okay. X with the little bar on the top, that was another way of saying mean. So this player had an average score of 15 points a game. Okay, down here is your median, and that was also 15. And then to get the range, I'm doing the max, take away the min, and that's 5. Okay, now the standard deviation is sigma. So there's our sigma symbol. It's 1.41. That's your standard deviation. Okay, so what's this tell you about this player? if this player played the next game, how many points would you expect them to score? Within what?
Like 10 to 20.
Say it again?
Like 10 to 20.
No.
15.
Okay, 15's the average. So this much above the average. So that would be like 16 and a half. Well, we know you can't score half a point. So we could say, well, between, 17 and 13. Right. Most likely he would score, or she would score between 17 and 13 points. That's sort of like 2 above the mean and 2 below, roughly. That's the numbers telling you. So this guy's scores or girl's scores are all pretty close to the average because that's a pretty small standard deviation. Okay, now if you're a guy or girl, there's a lot bigger difference. So all you got to do on your calculator is go stat, calc, one variable statistic, and change that to L2. So I'm going to go second 2, and now it's changed. Calculate the stats, bam. L2, no frequency list. There's your data. So even though this person had the same sum, 150, had the same average, 15, had the same median, let's see, I gotta go down, 15. Okay, the range would have been, let's see, the high take away the low. So 39 take away 0. And then this standard deviation is 11.5. So for this person, you got a huge standard deviation. So you don't know what's going to happen. This player is either hitting everything, he's got or she's got the hot hand, or this person couldn't hit water if they fell out of a boat. Because they're either scoring somewhere between 26 points and 3 points. You just don't know which one. Whereas player A is kind of your steady scorer. Okay, so if you were using these analytics, you could say, well, you know what? When I need a reliable point scorer, that's probably going to be player A. And when I need to create some sort of change, like I'm down by 17 points and I got 10 minutes to go, I need someone, hopefully player B has got the hot hand. And I can make up the difference. So that's the different, and we're able to compare these two guys because these means are the same. They don't have to be the same, they just have to be close to the same. So the factors that you need to take into account to compare them is they have to have close, the medians have to be close. Relatively close means. If these weren't both, if one was 15 and the other one was like 20, then we can't really look at the standard deviations. Okay, so that's how you do, so your whole assignment is really going to be plugging these into your calculator. All right, so for tomorrow, you're going to do this assignment. It looks like a lot, but it's really just plugging it into the calculator. So on this part right here, you're just going to use a single list. So I'm just going to type it, a single list of numbers. Single list, then hit compute or calculate. Okay, now these are frequency distributions. So when you have a frequency distribution, list 1 is the values and list 2 now is the frequency. So to calculate the standard deviations for these, you're going to be using 2 lists. Okay? Now, when you get to C, you've got intervals. So what you're going to do is your first list is going to be the midpoints of each interval. So let's see, halfway between 0 and 10, 10 and 15, and then your second list is going to be the frequencies. So when we have intervals, we use the midpoints. So if I was doing C, my list 1 is just going to be the midpoints of each one of those intervals. So 5, 15, 25, 35, 40. And then the second list is going to be the frequency of each one of those. Clear. And that's 18, 6. And then it's just stat, calculate. Okay, the values are in L1. The frequency list is in L2. And then I calculate. So for part C, my average is 20.2. And my standard deviation is 12.4. So this one would be, my average was 20.2. And my standard deviation was, what was it again? 12.4. So that's what you're doing on all these guys. It's really straightforward. This would be a single list. How much each one of these baseball players makes in 2017. Look at that. $91 million. It's crazy.
Look, I don't like it.
So there's all your lists that you need.
Okay.
Now you just gotta type them in and hit calculate.